Take some time to read this comic. Why did the guy in this frame, why did he continue going in the same direction? Why did he fall off? What law? If you said Newton's first law, you're right, because Newton's first law gives us a hint at what we call inertia. So let's look at inertia and mass. Inertia is the natural tendency of an object to resist changing state of motion. This is called inertia. For example, if an object is moving, it likes to keep on moving. If an object is stationary, it likes to remain stationary. It takes some measure of force to change this tendency. Are there some objects capable of resisting change better than other objects? Go ahead and list those objects after you've taken notes on the right side of your Cornell Notes. Think about objects that are capable of resisting change. And yes, the more mass an object has, the greater its ability to resist change. For example, a big guy is going to be much harder to push over than a small guy. And a large car is going to be much harder to change than a small car. Think about this. Who's going to win in a head-on collision? A little tiny Kia Sophia or a Ford F-350 truck? It's going to be the truck because it has a lot more mass. It's going to be much harder to change its acceleration. Check out my mass. I have a lot of inertia. But remember, the larger your mass, the more inertia you have, the more inertia you possess. So these are your questions, and I want you to not put these in your notes. So you put the notes on page 9, and you're going to put this now on page 8. Imagine a place in the cosmos far from all gravitational and frictional influences. Suppose that an astronaut in that place throws a rock. What do you think will happen to the rock? Will it gradually stop, or will it continue in motion in the same direction at a constant speed? When you answer these questions, I want you to do so in a complete sentence. So if you picked B, which is the correct answer, you would write, if a scientist was in the cosmos far away from gravitational and frictional forces and he threw a rock into space, the rock would continue in motion in the same direction at a constant speed. Now I know it's annoying to write incomplete sentences, but complete sentences equal complete thoughts, and we need to write down everything we know. So this will go under question 2 on the left page. A 2-kilogram object is affected by balanced forces. A 2-kilogram object affected by balanced forces is moving horizontally with a speed of 4 kilometers a second. How much net force is required to keep an object moving at that direction? So nothing, zero, nada, 0 newtons. Let's go back. Let's illustrate this. If an object is moving at 4 meters per second and there are no gravitational frictional forces, how much force is needed to keep this object moving at this speed in this direction? Well, the answer would be no extra force because it's already moving in that direction. And Newton's first law says, remember that objects want to just keep doing what they're doing. So if there's no friction, I'm going to do it like that. If there's no friction pulling it this way, then it's going to keep going in this direction at this rate or this speed until an outside unbalanced force acts upon it. So an object in motion will remain in its state of motion. The presence of an unbalanced force changes the velocity of the object. What is velocity? If you said it's speed with a direction, you're correct. So an example could easily be 4 meters per second north. So we have a speed and we have a direction that it's traveling. Question number 3. Mac and Tosh are arguing in the cafeteria. Mac says that if he flings the jello with a greater speed, then it would have a greater inertia. Tosh argues that inertia does not depend on speed, but rather upon mass. Who do you agree with? Explain Why? Do that in your notes on the left sheet of paper, page 8. Tosh is correct. Inertia is that quantity which solely depends on mass. So remember that solely means on mass. So as mass increases, my inertia also increases. And if mass decreases, my inertia will decrease. If we're talking about mass and speed, then we're talking about a factor called momentum. And that is something we'll discuss in physics, more likely in high school. But inertia or momentum is always looked at as a lowercase p. And so we'd have p equals the mass times the velocity. Question 4. Suppose you're in space in a weightless environment. Would it require force to set an object in motion? So if we're in a weightless environment, no friction, no gravity, is it going to require a force to make an object move? Absolutely it is, okay? Because inertia works even in space. Newton's first law works even in space. If an object in space is at a rest, then it's going to take a force to move it. So even in space, objects have mass, and if they have mass, then they have inertia. That is, an object in space resists change in its state of motion. A force must be applied to set a stationary object in motion. Newton's laws rule everywhere. Question number 5. Mr. Weightley spends most Sunday afternoons at rest on the sofa watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? This is a multifaceted question, so I want you to really explain what's going on here. So what Weightley's doing is he's increasing his inertia because he's just sitting there eating. He's adding more mass to his body, and therefore Mr. Weightley will increase his mass if he makes a habit of eating and lying on the sofa. And if his mass increases, then so does his inertia. So the longer he spends on the couch, the more force is going to be required to get him off the couch. Question 6. Ben Too Close is being chased through the woods by a bull moose, which he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating, yet if Ben makes a zigzag pattern through the woods, he will be able to use the large mass of the moose to his own advantage. Explain in terms of inertia and Newton's first law of motion what's going on here. Why can Ben, even though Ben is lighter, outrun the huge moose if he just zigzags? The large mass of the bull moose means that the bull moose has a large inertia. Therefore, Ben can more easily change his direction, his own state of motion, and make quick changes, while the moose has extreme difficulty changing its state of motion. So it takes the bull moose more effort to change direction because he has so much more inertia. He's so much heavier. And imagine it like this. If you're running at the wall full speed and you stop right before it, compare that to running at a wall full speed, stopping at the same point, but this time you're carrying 2 arms full of books. Which is going to be harder for you to stop? It'll be when you're carrying the books, because more mass equals more inertia, so it's harder for you to change direction. Let's look at balanced forces. Alright, so if you have a physics book or a science book on a table, gravity is pulling the book downwards, but the table is pushing in the opposite direction on the book, and therefore your book appears to not move, but forces are still acting on the book. Because the book is completely balanced, because the table pushing upwards on the book equals the gravity pulling downwards on the book, we have a balanced force. We call this a normal force. The book is said to be at equilibrium since there are no unbalanced forces acting upon the book, and it maintains its state of motion. It still sits on the table. If you knocked into that book, would the forces still be balanced? Probably not, because you moved the book. You made the book accelerate. Any change in acceleration is an unbalanced force. So let's say you're standing on the ground. Since the floor pushes upward on you as gravity is pulling down, you're at equilibrium. So there's this little person, it's probably me when I was little. I'm getting pulled down by gravity, but the floor is supporting me. So the floor pushes upward on me. What happens if gravity pulled down harder than the floor could push up? What would happen to me? Again, what would happen if gravity is pulling down on me more than the floor is pushing up on me? Good. I would sink into the ground. I would sink straight through the ground. The earth wouldn't be able to support me. So going back to the book example, let's say you give that book on the table a push. Well, the book is temporarily going to go into motion, but the friction from the table and gravity doesn't allow it to go very far. So when the book is resting, it's balanced, and it is in equilibrium, and it's not accelerating. When I push it, and the book speeds up, and then gravity and friction slow it down, all of that was acceleration. So it was unbalanced, but then it goes back to a rest. It goes back to rest and goes back to balance. So the book at first is balanced. When I push it, it becomes unbalanced. And then when it stops, it becomes balanced again. So I go from balanced to unbalanced to balanced. Special thanks to the Physics Classroom website, which was used to prepare this lesson. And you guys just got smarter.